Ready to go beyond the basics of deep learning? In this video, we're diving deep into advanced neural networks. We'll break down the complex mathematical foundations behind modern neural network architectures and show you how they're used in powerful real-world applications. If you want to understand advanced deep learning in practice, this is the video for you. What is deep learning? Neural networks. A specialized subfield of machine learning using multi-layered neural networks. Data abstraction. Learns complex representations through multiple layers of abstraction. Wide applications. Powers advancements in vision, language processing, audio analysis, and generative AI. Neural network foundations. Input layer. Receives raw data and standardizes it for processing. Hidden layers. Multiple processing stages extract increasingly complex features. Output layer. Produces final predictions or generations based on learned patterns. Convolutional neural networks. Pooling layers. Reduces dimensions while preserving information. Feature maps. Extracts patterns via convolutional filters. Object recognition. Identifies complex objects in images. Used in self-driving cars to detect pedestrians, traffic signs, and road conditions. Medical applications include tumor detection in scans. CNN applications. Medical diagnostics. CNNs analyze medical images to detect abnormalities with greater accuracy than human doctors. Facial recognition. Systems identify individuals by extracting unique facial features through convolutional layers. Satellite imaging. Remote sensing applications use CNNs to monitor crop health, urban development, and natural disasters. Recurrent neural networks. Input sequence. Processes data one element at a time. Hidden state. Maintains memory of previous inputs through internal state. Prediction. Generates outputs based on current input and memory. State update. Updates memory with new information for next step. RNN Mathematical Foundation. Hidden state formula. H sub t equals tanh of w sub h multiplied by h sub t minus 1, plus w sub x multiplied by x sub t, plus b sub h. The current hidden state depends on previous state and current input. Output calculation. Y sub t equals w sub y multiplied by h sub t, plus b sub y. Output is generated from the current hidden state through linear transformation. Vanishing gradient challenge. Long sequences cause gradients to become extremely small during backpropagation. LSTM and GRU variants address this limitation. Generative adversarial networks. Generator network. Creates synthetic data samples from random noise input. Learns to produce increasingly realistic outputs over time. Takes random noise as input. Produces fake samples. Aims to fool discriminator. Discriminator network. Evaluates whether samples are real or fake. Acts as a continuously improving critic. Takes samples as input. Outputs probability of being real. Aims to correctly classify samples. GAN applications. GANs create photorealistic images, videos, art, and synthetic data for training other AI systems. They power creative tools and data augmentation techniques. Latent space models. Encoder. Compresses input data into lower dimensional latent representation. Latent space. Compact representation capturing essential data features. Decoder. Reconstructs original data from latent representation. Sampling. Generates new data by sampling from the learned distribution. Diffusion probabilistic models. Forward process. Gradually adds noise to training data until it becomes pure noise. Creates a path from data to noise. Noise prediction. Neural network learns to predict the noise added at each step. Model is trained to identify noise patterns. Reverse process. Starting from random noise, gradually denoise by reversing the process. Creates new data samples from scratch. Model comparison. CNN. Key strength. Spatial pattern recognition. Primary application. Image analysis. Computational need. Modo 8. RNN. Key strength. Sequential data processing. Primary application. Text in time series. Computational need. Modo 8. GAN. Key strength. Realistic content generation. Primary application. Creative synthesis. Computational need. High. VAE. Key strength. Meaningful data compression. Primary application. Anomaly detection. Computational need. Modo 8. DDPM. Key strength. High quality generation. Primary application. Text to image. Computational need. Very high. Industry applications. Healthcare. Disease detection in medical imaging, drug discovery, personalized treatment recommendations, and patient monitoring systems. Finance. Fraud detection, algorithmic trading, risk assessment, and customer service automation through intelligent chatbots. Retail. Recommendation systems, inventory management, customer sentiment analysis, and automated visual merchandising. Entertainment. Content creation, special effects, personalized recommendations, and interactive gaming experiences. Implementation challenges. Data requirements. Deep learning models need massive datasets. Computational resources. Training requires specialized hardware. Hyperparameter tuning. Finding optimal configurations is complex. Interpretability. Models often function as black boxes. Future directions. 100 times efficiency gains. Expected improvement in computational efficiency over next decade. 10 billion plus parameter count. Size of largest models by 2025. $1 trillion market impact. Projected economic value by 2030. Future research focuses on more efficient architectures, multimodal learning capabilities, and models that require less supervision in data. Don't miss our upcoming session on natural language processing. Be sure to subscribe, like, and share so you're the first to watch it.